Okay, maybe we can start now. So
Yeah.
welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today's first speaker is Jacob Gunn from University Napoli in Italy, and he's going to talk about phenomenology of primordial black hole hotspots. I'll
Yeah.
send you a reminder when 5 minutes are left.
Okay, fantastic. Yeah, so thanks very much for the opportunity to speak here. I'm going to tell you about the phenomenology of primordial black hole hotspots, which is based on the work I did with collaborators at Durham University, primordial black hole hotspots and out of equilibrium dynamics. Okay, so what are primordial black holes? Primordial black holes are black holes which form in the primordial universe from the collapse of overdensities, rather than from the collapse of stars at late times. So unlike astrophysical black holes, there's no Chandrasekhar limit on their mass. So primordial black holes can form with initial masses ranging from 0.1 grams to 10 to the 20 solar masses. The initial mass is going to be called m-ini pbh throughout this talk. Heavier primordial black holes in the so-called asteroid mass range, around 10 to the 15 grams, could make up all of or part of the observed relic density of dark matter today. And as I'll show in this talk, lighter primordial black holes could have played important roles in key cosmological phenomena such as baryogenesis and dark matter production. Primordial black holes form when overdense regions of the early universe exceed a collapse threshold. This requires huge densities. Density contrasts on small scales. Solar mass primordial black hole would take order, I missed a slide here, would take order 10 to the 18 grams per centimeter cubed in order to form. So the question is, how could such large overdensities form in the early universe? Okay, and there are many proposed formation mechanisms of primordial black holes. For example, the collisions of bubbles during first order phase transitions could form primordial black holes when the high density bubble walls overlap. That's illustrated in the left figure here. The mass of the produced primordial black holes depends pretty much only on the temperature at which this phase transition occurs. And so you end up with a monochromatic mass distribution, which is to say that all of the primordial black holes have the same mass when they form. Alternatively, some cosmological models predict the formation of networks of topological strings throughout the universe, and it's possible that when the strings form loops, if there's enough energy contained within that loop, the loop can collapse to form primordial black holes. This model is much more model dependent, and you typically get extended mass distributions where primordial black holes have a range of masses. By far, the most important and most studied mechanism of primordial black hole formation is inflationary overdensity collapse. So in the left figure here, I'm showing an inflaton potential, which has an ultra slow roll feature over here. Potentials with kinks or bumps or in multi-field inflation models can produce inflationary power spectrums, which are greatly enhanced at small scales. The inflationary power spectrum, like the one I'm showing in the right plot here, tells us how much power is in perturbations of different scales. So when you have a large increase in power at small scales, which corresponds to a large wave number k, like you have in this power spectrum here, you get a universe with lots of small scale high density spikes. We know from the CMB that the large scale power spectrum should be quite flat, but the small scale power spectrum is largely unconstrained. And the idea is that when the wave mode K re-enters the cosmological horizon, it might collapse and produce primordial black holes if it's powerful enough. In fact, this is not a generic feature of inflationary models. A wide range of models do predict primordial black hole formation, but most of them require some fine-tuning of the parameters in order to abundantly produce primordial black holes. When primordial black holes form, they form with a particular initial abundance, which is denoted as beta, and essentially the ratio between the energy density which collapses to form primordial black holes and the total energy density in the universe when they form, which is rho critical. In various plots, you'll also see the quantity beta prime occur, which is just beta rescaled by the square root of this gravitational collapse factor, which is about 0.2. So those are the same thing. Primordial black holes also form with a particular initial mass, and this is related to the horizon mass at the moment of formation. The horizon mass is the total mass contained within the cosmological horizon, which is itself defined by the distance that light could have traveled since the beginning of the universe. So, as the universe expands, the horizon mass grows linearly with time, which means that heavier primordial black holes form later. You can see that in the figure that I'm showing here. I'm plotting the temperature at which primordial black holes would form as a function of their initial mass. I mean, obviously, heavier primordial black holes form when the universe is older and cooler. And I'm illustrating with vertical lines here some interesting cosmological phenomena and the masses that they coincide with. You have the Pecke-Quinn phase transition, electroweak phase transition, QCD phase transition, and Big Bang nucleosynthesis. So even the heaviest primordial black holes form in the radiation-dominated universe, with solar mass primordial black holes and lighter forming in the symmetric Higgs phase. If primordial black holes were to form during an early matter-dominated era, they might form with angular momentum. For the remainder of this talk, however, I'll assume that primordial black holes form in the radiation-dominated era and so have vanishing angular momentum. Therefore, along with the initial mass, the initial abundance completes the parameter space of primordial black holes. So a cosmological population of primordial black holes is described completely by the initial mass and abundance of the primordial black holes. Here, I'm showing a relatively recent summary of existing constraints in that parameter space. Primordial black holes heavier than about 10 to the 15 grams at formation would still exist today and are subject to various constraints. You can see constraints from the CMB, gamma ray non-observation, and the non-observation of gravitational lensing events. Lighter primordial black holes would have evaporated completely by today and are subject to constraints from BBN in the mass range 10 to the 8 to 10 to the 10 grams, but even lighter primordial black holes are almost entirely unconstrained. The Planck, LSP, and entropy constraints that you can see in that mass regime are all highly model dependent. And however, in this mass range, they are increasingly subject to gravitational wave constraints. So one of the most fascinating features of primordial black holes I just alluded to is that since they can take very small masses, they might essentially explode in the early universe. This was famously pointed out by Hawking in 1974. He showed that all black holes produce blackbody radiation and slowly lose their mass at a rate proportional to the inverse square of their mass. This means that for stellar mass black holes, this is essentially unobservable. We should expect to never see this from a black hole forming from a star collapse. However, since primordial black holes can be much lighter, and especially at the end of their life when they've already radiated away some of their mass, the evaporation can be extremely rapid. It's important to note that primordial black holes produce all available degrees of freedom, even beyond the standard model ones. So light primordial black holes would produce rapid bursts of high energy particles in the early universe at a black body spectrum with a temperature TBH, which is inversely proportional to the primordial black hole mass. This is the black hole surface temperature. The late time nature of this evaporation is currently under debate in the literature. Some authors suggest the semi-classical evaporation proved by Hawking should be damped after the black hole radiates away around a half of its mass. So here I'm showing a schematic of how you might think about Hawking radiation. If you're familiar with the concept of pair creation, you can imagine a pair of particles which is created near the event horizon of a black hole. One of the particles moves towards the black hole, the other with opposite momentum moves away from it, and the infalling particle decreases the mass of the primordial black hole. It's treated as having negative mass, so the primordial black hole loses mass, and the other particle escapes out into the universe as Hawking radiation. The remainder of this seminar will be concerned with primordial black holes which are in the ultralight mass range. Those are primordial black holes which have mass of less than about 10 to the 9 grams. And these primordial black holes evaporate completely before Big Bang nucleosynthesis start. So they're impossible to detect directly. However, their life cycles are cosmologically contemporaneous with critical processes such as baryogenesis, dark matter, and the QCD and electroweak phase transitions. As we'll see soon, they also produce hotspots with extreme temperature gradients. Due to Hawking radiation, cosmological populations of primordial black holes evolve in an interesting way. First of all, black holes redshift like matter, that is proportionally with the inverse cube of the scale factor. Meanwhile, radiation redshifts with the inverse fourth power of the scale factor, so the relative density of black holes in the universe compared to radiation grows with the scale factor. Eventually, the primordial black holes may become the dominant component of the universe. And you can see this in the top panel of the figure that I've got here. Oops. In the dashed line is the relative density of radiation, and the solid line shows the relative density of primordial black holes. Initially, radiation dominated, the universe evolves and expands, and the primordial black hole relative component grows and eventually becomes the dominant component in the universe. So eventually the primordial black holes evaporate completely and radiation domination rather, is quickly restored at the end of the primordial black hole life. This carries with it a huge dump of photons in the universe, which increases the entropy of the universe. And you can see this in the bottom plot that I'm showing here, where the entropy is shown as a function of the time. And you can see that at the end of the primordial black hole life, the entropy of the universe gets this big dump of entropy into it. And this occurs according to the equation that I have at the bottom. Okay. So such a large entropy dump also reheats the universe. And here the figure is showing the evolution of the temperature of the universe with respect to the scale factor. When the primordial black holes evaporate, they heat the universe. And until recently, all analyses assumed that the universe was heated by primordial black holes homogeneously, with the temperature increasing everywhere by the same amount. You can see that as the kink in the otherwise linear evolution here. The primordial black holes heat the universe and slow its rate of cooling around here. However, recent studies show that this picture is not correct, because primordial black holes do not evaporate in a vacuum. Ultralight primordial black holes evaporate in a universe which is already extremely dense and hot, brimming with particles. Hawking radiation ejected into the hot thermal bath eventually interacts with its surroundings. Since Hawking radiation is always boosted with respect to the background universe, when it interacts, it deposits energy into the plasma. So one can show that the LPM suppressed collinear emission of soft gauge bosons is the dominant mechanism by which this occurs. And this occurs with the rate gamma LPM, which is shown by this equation here, and crucially depends on alpha squared, which is the gauge coupling of the particle. Here, T is the temperature of the background universe, and K is the momentum of the Hawking radiation, typically of the order of the black hole temperature. So a particular rate, gamma LPM, corresponds to a particular length scale. And it seems that primordial black holes are depositing energy into their surroundings a particular distance away. That length scale is given by the inverse of the rate, and I'll call it R core for reasons which will become immediately obvious. The energy deposited into the plasma will now diffuse both outwardly and inwardly back towards the primordial black hole. The typical time that it takes to random walk the length R core back to the primordial black hole is given by the 1D random walk equation shown here, where TEL is the timescale of elastic scattering in the plasma. It takes time TD to random walk back to the primordial black hole. And if that time is much less than the timescale of the evaporation of the primordial black hole, then the diffusion of the energy deposited back towards the primordial black hole is efficient, and it smooths over the temperature distribution close to the primordial black hole. So this is depicted schematically by the figure. Hawking radiation travels a distance R core. This is called RC, sorry, this is called TTH in this diagram, or RCR over here. They're the same thing. And it heats a shell at that distance away from the primordial black hole. The energy in that shell then diffuses both outwardly and inwardly, and in the inward direction forms a smooth core with a constant temperature close to the primordial black hole. And this core might be hotter than the temperature of the surroundings. And the result is a hotspot with a local temperature gradient. The energy deposited in time TD forming a sphere of constant temperature around the primordial black hole given by this equation here. Note that the temperature of the core is always around 4 orders of magnitude smaller than the temperature of the black hole. Okay, so the figure here shows the relevant temperatures and how they evolve. The primordial black hole temperature in red sets the hotspot core temperature in green. Initially, the temperature of the background universe, which is the purple line, is hotter than the temperature of the would-be core. So there's a primordial black hole, which is evaporating, but it's not yet able to form a hotspot. As the universe expands and cools, eventually the hotspot core temperature is hotter than the background universe, and so the hotspot emerges. The evolution of the mass is at this point slow, so the core temperature remains relatively constant while the background universe cools around it. At the very end of the primordial black hole life, the evaporation really speeds up and the core temperature heats up as well. And you can see that in the upward trend towards the end of this graph. So outside the smooth core, the hotspot temperature profile falls with the inverse cube root of the gradient, where the universe remains in thermal contact with the primordial black hole. At the very end of the primordial black hole life, some regions may be frozen out of thermal contact with the primordial black hole if the evaporation rate becomes too small. And that results in this different gradient that you see here with a gradient of r to the power of -7/11. Very far from the primordial black hole, the temperature of the background universe is recovered. And you can see that in the flat region in the very far regime from the primordial black hole. It turns out that the maximum temperature of a hotspot is actually independent of the initial mass of the primordial black hole and is around 2 billion GeV. That's the maximum temperature you can have in the core. The profile can be expressed formulaically as shown here. Each of the quantities appearing in the expression are a function of the primordial black hole mass, time, or both. So recall that the primordial black hole temperature sets the core temperature. And so any two primordial black holes with the same instantaneous mass have the same core temperature, regardless of what their initial mass was. However, only those which start with the same initial mass have identical profiles. So the primordial black hole hotspot evolves with time and depends on the initial mass. So the evolution of a hotspot is driven initially by the cooling of the background universe. The primordial black hole mass varies slowly at first, and so the core temperature remains approximately constant. Here, the solid and dashed lines show the profile at two relatively early times in the primordial black hole life. The core temperature doesn't change much, but the background temperature cools in the dashed line by about an order of magnitude, and so the hotspot profile is extended. At very late times, the primordial black hole evaporates much more rapidly and heats up. This causes the core temperature to rise significantly. The dotted line here is showing the primordial black hole profile near the end of its life, where note that compared to the dashed line, the universe hasn't cooled very much, but the core temperature has heated up significantly. So this really is a rapid process at the end of the primordial black hole life. Okay. The profile we've discussed so far results from taking a fiducial value for the gauge coupling alpha equal to 0.1 for all species. In reality, different species will have different gauge couplings, and there will be some amount of speciation within the hotspot where particles are distributed according to their gauge couplings and mass. In particular, it's interesting to ask what happens to particles with very weak couplings. Very weak gauge couplings in particular. These particles don't see the LPM effect at all. And so you would expect them to travel through the hotspot in a completely different manner. Later, we'll look at the examples of right-handed neutrinos and dark matter. In order to understand how gauge singlet particles move through a hotspot, our starting point is the mean free path. So a particle X is traveling radially outwards from the primordial black hole. The mean free path of X is usually defined as the inverse of the total interaction rate of X. And we might suppose that the interaction rate can be decomposed into a decay rate plus a scattering rate. The decay rate for the channel X goes to Y and Z will be given by a coupling and some function of the masses mx, my, and mz, while the scattering rate will be given by the sum over the thermally average cross sections for all the relevant processes with respect to the black hole temperature and also the background temperature, and the number density of particles off which X is scattering. So all of the quantities that I've just mentioned, except the black hole temperature, are functions of the local temperature in the hotspot. In a hotspot, the local temperature is a function of radius. And so all of these quantities are also functions of radius. That means that the way that the mean free path is defined here is itself a function of radius. The definition of the mean free path, which depends on the radius, does not make sense. To go further, we define the probability that a particle propagates a distance r before interacting as the negative exponential of the integrated interaction rate between r and 0. R equals 0 corresponds to the origin of X, and then we can define the mean free path as the solution to P of R equal to 1/2. Therefore, the mean free path is understood as the distance beyond which X is more likely than not to have interacted with the plasma and deposited its energy. So given a particular hotspot profile, T of R, like for example, the one shown in the left plot here, we can calculate what the mean free path is for X by taking some particle physics model for X as well. We have to calculate the thermal masses, the kinematics, the number densities, and the degrees of freedom as functions of the temperature. And then knowing all that, we can calculate the interaction rate as a function of the radius, like I'm showing in the right plot here. The interaction rate is then integrated between 0 and R until the probability to have scattered is equal to 1/2, and we found the mean free path. Here I'm showing contours of the mean free path in the coupling versus mass plane for a right-handed neutrino. The dashed line here is a theoretical minimum, and the dotted and solid lines bound from below the regimes where the mean free path is within the hotspot and within the core of the hotspot. The lightest, most weakly coupled particles, the ones in this regime here, have a mean free path lying beyond the entire hotspot. In the rest of the parameter space over here, the decay rate is so strong that the particles decay close to the primordial black hole, actually within the core of the hotspot. And in the intermediate regime between these two lines, the mean free path lies somewhere in the outer regions of the hotspot. So it's clear from this graph that the way that a particle moves through the hotspot depends strongly on its particle parameters. And calculating the mean free path in this way required us to know the profile T as a function of R. The mean free path, therefore, gives us a quantitative picture of how Hawking radiation moves through the hotspot, but only at a particular instant in time. Hotspots evolve with time. At earlier or later times, the picture changes. So we need to account also for the time evolution of hotspots. In order to do this, the appropriate question to ask is, what fraction of x produced by the primordial black hole escape to a particular radius r? We can find out by integrating the equations for n escape and n trap over the whole primordial black hole life, and therefore the evolution of the primordial black hole hotspot is accounted for. NE here is a measure of cosmic time, the number of e-folds. This also requires us to choose a specific radius that we're interested in, r, and this will depend on the physics under study. So let's look at some phenomenology which will inform this decision. Since hotspots can have temperature profiles which rise multiple orders of magnitude in the temperature, it can be the case that in the cool background universe, a phase transition has occurred which has not yet happened in the hot core. This is illustrated by the figure where the background universe here is a few tens of GeV and the electroweak phase transition has already occurred. In the hot core, however, the temperature is a few hundred TeV, and so the electroweak phase transition has not occurred yet. Hawking radiation produced close to the primordial black hole appears in the symmetric Higgs phase. As it propagates outwards, its surroundings get cooler until it crosses into the broken phase. Remarkably, hotspots produce spatial boundaries between symmetric and broken phases rather than the temporal ones that we're used to in cosmology. A particle which is produced massless can gain mass simply by traveling away from the primordial black hole. As well as phase transitions occurring in the profile of a hotspot, so too can the freeze out of particle interactions and species. The figure here depicts two hotspots, where the yellow hotspot is produced by a lighter primordial black hole and so has a hotter core profile. In the hot core of the yellow profile, interaction rates are large and number densities are large because interaction rates are fast compared to Hubble. The radius at which the interaction rate becomes equal to Hubble is labeled RFO or R freeze out, and beyond this radius, the interaction is frozen out and occurs with vanishing probability. A particle which is trapped within R smaller than R freeze out scatters efficiently and thermalizes with the hotspot. However, if a particle escapes beyond R freeze out into the much cooler background, it will likely never scatter and it free streams in the universe. Note that in the purple, cooler hotspot, the temperature is below the freeze-out temperature everywhere, so RFO is not defined, and particles would always free stream. Okay, so phase transitions and particle scattering freeze-outs can inform the decision we make for the radius r in those equations. But there may also be other ways of choosing r, which we haven't considered. Let's now apply these considerations to leptogenesis, in which primordial black holes produce right-handed neutrinos. Okay, quickly, type 1 leptogenesis is a simple model based on the seesaw mechanism, which aims to generate the baryon asymmetry of the universe and explain neutrino masses. The standard model is simply extended by at least 2 or 3 singlet fermions, which are the right-handed partners of the standard model neutrinos. They're called N, also referred to as right-handed neutrinos. So the right-handed neutrinos are coupled to the standard model via a Yukawa interaction, which is depicted here as the decay of the right-handed neutrino into the standard model lepton and Higgs doublets. So leptogenesis relies on the decays or production of right-handed neutrinos to produce an asymmetry between leptons and antileptons. When the temperature of the universe is greater than about 130 GeV, leptonic asymmetry is efficiently converted into baryonic asymmetry by Sphaleron processes. So we denote this temperature T Sphaleron. At low temperatures, when the electroweak phase transition has occurred, in the broken Higgs phase, sphalerons stop being active. So no more lepton asymmetry is converted into baryon asymmetry at small temperatures. Only right-handed neutrinos which decay at high temperatures contribute. This motivates us to define R sphaleron. R sphal is defined as the radius at which the local temperature is equal to the temperature T sphal. The figure here again depicts two hotspots, the yellow being from a lighter primordial black hole and therefore having a hotter hotspot. In the yellow hotspot, the core temperature exceeds T sphaleron, and so R sphal is defined here. In the purple hotspot, the core temperature is below T sphaleron, and so R sphal is not defined. In both cases, the sphalerons have frozen out in the background universe, but in the yellow hotspot, sphalerons remain active in a sphere of radius R sphaleron around the primordial black hole. Right-handed neutrinos which decay within this sphere source a baryon asymmetry, while those which escape beyond R sphaleron never contribute to the baryon asymmetry. Therefore, the contribution to the baryon asymmetry from a primordial black hole is proportional to the number of right-handed neutrinos which are trapped within the radius R sphaleron, given by the equation we saw before. And the calculated baryonic yield, which is the cosmological observable associated with the baryon asymmetry, should be proportional to the number density of primordial black holes, the CP asymmetry, parameter epsilon, the Sphaleron efficiency, and it's normalized by the entropy S, which remember is also significantly produced by primordial black holes. Integrating this equation over the whole primordial black hole lifetime gives us the contribution to the baryonic yield from a primordial black hole. So in this plot, I'm showing the fraction of right-handed neutrinos which are trapped within R Sphaleron as a function of the initial mass of the primordial black hole which they're produced from, and for 3 different points in neutrino parameter space. So very light primordial black holes evaporate entirely before the universe ever cools to T Sphaleron. Therefore, R Sphaleron is never defined in this low mass regime here. Indeed, for the parameters that we choose here, we expect the washout of asymmetry to be very fast in this regime, and we would expect no contribution to the baryon asymmetry. So that's why it goes to 0 over here. When R Sphaleron is defined, heavier primordial black holes have cooler hotspots, which trap fewer right-handed neutrinos, and so the fraction drops with the mass. By far, the biggest contribution occurs for the most strongly coupled and heaviest right-handed neutrinos, which is the red line here, and which we expected from the mean free path considerations earlier. So here are the results in the primordial black hole parameter space, beta versus MPBH ini. The contours here bound regions where primordial black holes can produce the observed baryon asymmetry of the universe in their hotspots. It's interesting to note that the neutrino parameters that we choose here would not lead to successful leptogenesis without primordial black holes. And the primordial black holes that we consider here were previously thought to be unable to produce any baryon asymmetry because they evaporate primarily after the Sphaleron freeze out in the background. Furthermore, the strongly coupled points that we choose are potentially testable by upcoming experiments, which can only probe very tiny regions of the thermal leptogenesis parameter space. And primordial black holes in this region are potentially subject to upcoming gravitational wave detection experiments. So this scenario may be testable in the near future in a way that standard leptogenesis simply isn't. Had we done the analysis and ignored the effect of hotspots, we would find no successful region in this plane at all. It's clear then that accounting for the hotspots is absolutely crucial when considering Hawking radiation in the early universe. Next, we can consider the production of dark matter by a primordial black hole. We consider a simple WIMP-esque model of dark matter where fermionic dark matter psi is coupled to the standard model via a Z prime portal. The Feynman diagram shown here is for dark matter annihilation into 2 standard model fermions F. In the forward time direction, it destroys dark matter, and in the backward time direction, it produces it. And this is the primary interaction which keeps dark matter in thermal equilibrium in the universe. And it's controlled by 2 couplings, G dark and G visible, which couple the dark matter to the Z prime and the Z prime to the standard model respectively. At high temperatures, the rate of this interaction is much faster than Hubble, and dark matter has a thermal abundance. At low temperatures, the rate drops below Hubble, dark matter production slows compared to the annihilation, and soon after, the relic density of dark matter which we observe today freezes out. This occurs at the freeze-out temperature TFO, which corresponds to the radius within the hotspot, RFO. When dark matter is produced by a primordial black hole as Hawking radiation, if the core temperature is above the freeze-out temperature, as it is in the hotter yellow hotspot here, then dark matter may be trapped in the hotspot and thermalize with the hotspot. This essentially erases its contribution to the dark matter relic density. If, however, it escapes beyond RFO, it's unlikely to ever scatter, and it free streams in the universe, representing a new contribution to the dark matter relic density. Therefore, the contribution to the relic density produced by a primordial black hole is proportional to the number density of dark matter which escapes beyond the radius RFO. Note that this is the opposite case to leptogenesis, where the contributing particles were those which were trapped. So if we integrate this equation over the primordial black hole lifetime, we obtain the total number density which escape and contribute to the relic density. If the contribution to the relic density is too large, primordial black holes will overclose the universe. So we fix the dark matter parameters so that the correct relic abundance would be obtained in the absence of primordial black holes, and then ask the question, where in the primordial black hole parameter space would primordial black holes overclose the universe and be in tension with the WIMP dark matter model? This analysis has been done previously, but ignoring the effects of the hotspots. So here I'm showing the fraction of dark matter produced by a primordial black hole, which escapes beyond our freeze-out, and therefore will contribute to the relic density as a function of the initial mass. Very light primordial black holes have very hot hotspots, which efficiently absorb dark matter and prevent it from contributing. Heavier primordial black holes have cooler hotspots, so more dark matter escapes. The different colors here represent different masses of dark matter. And you might note that lighter dark matter, since it freezes out at a lower temperature, is more efficiently absorbed by heavier hotspots. Okay, so here are our results in the primordial black hole parameter space. The contours bound from below the regions where primordial black holes would overclose the universe with dark matter, and so would be ruled out in the WIMP dark matter scenario. The different colored lines, again, are different masses of dark matter, and here the solid lines are our results, including the effects of the hotspots. The dashed lines are the results that you would get if you ignored the effect of hotspots. So notice that the hotspots shift the contours towards heavier primordial black holes because, remarkably, the hotspots of light primordial black holes efficiently absorb dark matter. So this again underlines the point that doing accurate phenomenology of Hawking radiation requires quite a careful accounting of the effects of hotspots. And our results demonstrate that cosmological observables such as the dark matter relic density and the baryon asymmetry of the universe can be strongly impacted by the presence of hotspots. So before I move on to the outlook, I'll make the general remark that particle species which are extremely weakly coupled will easily escape from hotspots, and the effect of the hotspot is minimal. Those which are very strongly coupled will be very strongly affected. In any particle physics model, where the line is between these two regimes is not obvious, and it typically requires at least some calculation. Okay, so the work that I've discussed in this talk is the first of its kind to discuss the effects of hotspots on Hawking radiation. Understanding hotspots in detail will require much more work, and I've outlined here some possible directions that require further investigation. So all the physics that I've mentioned so far occurs before the primordial black hole stops evaporating. And what happens to the hotspot after the evaporation stops is much less understood. How hotspots cool, whether or not the universe ever properly diffuses the hotspot, and how structure formation might be affected are all open questions. Insofar as the formation of hotspots is concerned, it's not known how Kerr primordial black holes would form hotspots, which are primordial black holes with angular momentum. It's not known how speciation would really work, or how hotspots would form in the matter or dark energy dominated eras. Armed with our admittedly elementary understanding of hotspots, we might also revisit constraints on primordial black holes. In particular, gamma ray constraints on primordial black holes might be affected by hotspots absorbing gamma rays. It's not clear how hotspots would affect gravitational lensing constraints. And it's also not clear if hotspots might absorb neutrinos and suppress BBN constraints in the early universe. Okay, so I've come to my conclusions, which is the homogeneous heating approach to primordial black hole evaporation does not capture the effects of hotspots. Hotspots form soon after evaporation begins and may reach extreme temperature gradients. Hotspots have interesting phenomenological consequences, which can drastically affect cosmological observables, such as the baryon asymmetry of the universe and dark matter relic density. And finally, there's much more work that's needed to be done to understand hotspot physics at early and late times. Thank you.